All right, so we're recording again. Uh, Good afternoon, everyone. Thank you for attending our class today. We are continuing our discussion about normal distribution. In particular, we're looking at standardizing data. What does that mean? That's one of our objectives today. And we're looking at a formula that will standardize our data and change it to what we call a z-score. So that's our objective for today. Um, so let's take a look at some of the things we're planning to do. It's not going to be a very long discussion, although we will have a group breakout session today, and I'll explain it as we go along. I also would appreciate if you mute your mics. Unless you have a question, feel free to butt in and just ask me a question right away. Okay. So what's the goal for today? The goal for today is to review some of the things we've done so far regarding normal distributions. We'll try to describe and calculate what we mean by the z-score. So what does that mean? So that's something we haven't talked about in the past. We haven't heard about that. That's completely brand new. And we'll also try to calculate the area under the normal curve. We will be using two things. We'll use formula and StatCrunch technology at the same time. Okay, so those are our goal for today. Let's go. Major announcements, nothing much. Homework is still discussion board, module number 10. That's due on March 22. We won't have our packet check. As you know, we'll do it when we're back from the break. Well, this is not the break technically, from the online version to a face-to-face version. Uh, we're technically in mod 12.3 to be exact. I think we did 12.1 to 12.2 last time. So this was last time. Um, and so let's go do a little bit of review, starting with the first always, sometimes, never question. Okay, so just let me know if you have some questions. All right, so the first one is always, sometimes, or never. So we're given a normal distribution and we were given a mean of 10. So remember, this is our mean and we signify that as mu, that is pronounced as mu. It's a Greek letter, kind of like a U with a little bit of a front end thing here. And this is the population standard deviation. So that's the standard deviation. We call it sigma. Okay, so it's kind of like an O with a little bit of a bangs over there. So the question is, if we do have a normal distribution centered at 10, so this is our mu, which is equal to 10, and our sigma is 5. So it starts to spread from the center outwards by 5 units, which makes this part 10 plus 5, that's 15. This is 20. This is 25. And this is 5. 0 minus 5 again is negative 5. Then the unusual values, which is the main keyword here, is between or are between 5 and 15. So guess these are 5 and 15. So is this always, sometimes, or never? If anyone knows it, please tell me. So it's, corny if I always say the right answer. Okay, somebody said never. Yeah. Okay, why? Why never? Okay. So remember, this one, we call this typical values. That's the bulky part. Majority. So those are typical value. Our typical values. Our unusual values are beyond the second standard deviation. So right here on the unusually high tail, and this is the unusually low tail. For it to be considered unusual, it has to exceed or go beyond the second standard deviation, because the first two standard deviation will be about 95% of the data. Ugh. That was annoying. So this is 95% of the data from here to the end of the second standard deviation. So everything there is 95%. Okay. The unusual part would be the last 5%, which is shared here and there. So about 2.5% each. Okay, so let's take a look at the next one. Unless you have questions, just let me know. Oh, next, always, sometimes, never question. A normal distribution is symmetric, bell shape, and a very fancy word here with a point of inflection coinciding the first standard deviation. Okay, so definitely we know it's symmetric and it's bell shape because we've been using those descriptions of the normal distribution for a while now. Well, the bell shape is relatively newer. Oh, well, not really relatively newer. No, the word normal distribution was relatively newer, but we know it's essentially a symmetric bell-shaped graph. Now, what is this point of inflection here? This was one of the book definition from last class. It says that, well, if this is the mean, and you move one standard deviation from the mean. So this is mean plus one standard deviation. And this is mean, take away one standard deviation. There is a point here, and the claim of the statement is that is the point of inflection. In algebra, a point of inflection is a point where the graph tends to switch what we call concavity. So this is a concave up. It's kind of like a smiley face, though this is concave up. And this side is concave down, kind of like a sad frowning face. So what it's saying is, this is a concave up. There's a point of inflection there. It becomes concave down. This is a concave down as well. And then there's a point of inflection. This is a concave up. That actually is true. That's always true. When you reach the first standard deviation, that is exactly the same portion, or it marks the point here as a point of inflection. Okay, so we're not going to be focusing too much on this, but I thought this was one of the things that was mentioned last time. All right, let's move on to the next one. Do you have any question about that? So we're not really interested in this vocabulary in the long run. Okay, so the area. This one is more of a concept type of question. The area under the normal distribution N12 1.5 is bigger or has a bigger area compared to N10 1.5. So we do have a normal distribution. It does have a center, mu equals 12. We're comparing that with another normal distribution, but the measurement of the center is a little bit lower. It's 10. They do spread about the same way. So it's around 13.5, and keep on adding that and subtracting it here. Now this is 11.5 plus 1.5 plus 1.5, and then 10 minus 1.5 minus 1.5 again. We only mark up to the third standard deviation. All right. The question is the area here, everything here, bigger compared to the area here, which is everything there, simply because their means are not the same? Any guesses?
Would it be always?
Okay, always true. Why do you think so? Will the mean affect it? Oh, it's just a guess. Okay, anyone else? Any other guesses?
I say
Okay.
always too.
Always true also. Okay, it sounds so commonsensical, right? Like the higher the mean, it would give you higher numbers. But the thing is, this is actually never.
What?
Why is that number? Okay, first of all, we talked about probability distributions before. We know that the area under the curve is worth 100%. Okay, so this should be 100%, and this should be 100%. Regardless whether your normal distribution is very flat like that or very tall. It's like a balloon. If you have like a water balloon with water inside of it, or air, you can stretch it out or you can compress it. It will deform the balloon, but the amount of air or water inside it won't change. It's the same amount of space inside the balloon. So we can like stretch it up like this or stretch it sideways or move it from one center to another center, like move it to a different center which is a little bit lower, so it's now there. The area will never change. It's always 100% of all the data, because remember, the distribution, it represents amount of data. Differing the center does not affect the percentage of the data. Okay, so that's a never.
Wait,
They're
so
the
that
same.
means
Yeah,
so that means that it's all equal to 100?
it's always going to be equal to 100. Yes, remember probability distribution from last class, they always add up to 100. Okay, good. I'm glad I kind of settled that. A little bit of a review from last class as well. We did talk about what are considered typical values. We loosely call this the bulk of the data. They form about 68% or within one standard deviation. So if you have your normal distribution here, from the center, one standard deviation up and one standard deviation down, this area here is 68%. That's majority. That's above 50%. That's majority of your data are within one standard deviation. Now, the area here and here starts to go lower and lower or the number of amount of data there becomes less and less as you move towards the end of the tail. Um, Unusual values, on the other hand, they are two standard deviations above or below the mean. So let me switch color marker. So if this is the second standard deviation, so that's the mean plus two pieces of standard deviation. And then you move again one standard deviation here. So minus two standard deviation already. Now this portion here, I'm coloring gray. Those are unusual values. For this side, this is considered unusually high. For the other tail, we usually call this unusually low. How so? How many percentage is confined within two standard deviation from our last discussion? Do you remember that? So how much percentage are here within two standard deviation? Remember, we had an empirical rule, which is 68 for the first standard deviation, 95, and 99.7. So for two standard deviations, there's already 95% of the data found within two standard deviation. That's almost everything. There's still 5% left over. The 5% left over, just like what I've mentioned earlier, will be shared by the tail. They get 2.5% each. So 2.5% of the data are considered very, very high, unusually high, and 2.5% here are considered very, very low. So this is particularly true for looking at strange sickness. There are certain sickness that only exists in like 1 in a billion or one like less than 10 in the whole population of the world. So they're definitely unusual cases. You don't see them here in the general population. Those unusual cases will kind of like pop up in portions of the population, like usually low numbers of the population. Okay, so moving on, just a little bit of a review. Random variables are quantitative variables, and we actually kind of like want to include the word random there, because when we gather data, uh, especially when we're doing like research or projects or an experiment, when we gather data, uh, they don't necessarily are predictable type of information. What do I mean by that? For example, if you're selling chocolates and you're trying to count how many pieces of chocolates each of the customer buys, you, for every person in line going to the cashier, you don't know whether they're carrying 2 pieces of chocolates or 4 pieces of chocolate, maybe just 1 piece of chocolate. So those are random results. You do get quantitative answers because we're counting number of chocolates, but they're considered random variables because there is an element of a surprise in it. We don't know how many chocolates each customer buy, so they're not like robots that we can just assign them. They're like, they have their own preference on the number of chocolates. So anything that we discuss from here onwards, in particular, when we're kind of like trying to get a sample or an information from the population, they tend to be random. So that's why we call them random variables. All right. If you have your handbook with you, this is the best time to actually go and start looking at this new topic. And we'll start with standardizing scores. Okay. All right. So, what do we mean by standardizing score? In statistics, a standardized score measures the distance between the value and the mean using standard deviation. So, when you have a standardized score, we look at your original value. We often use variable x for that. And we also look at the mean. Okay. Also look at the mean, because the mean is found straight at the center of the distribution. Your x is a random variable, so it could be anywhere. It could be anywhere. It could be from the extreme end. It could be at the mean. It could be less than the mean. It could be more than the mean. If this is 10, so an x could be 15. It could be 2. So because it's random, it could be anywhere on our normal distribution. It can be found anywhere. But to standardize the score, it means we find the distance of your x from the mean. So how far is this distance? And that is measured in terms of standard deviation. So for example, to make this more or make this clearer, suppose that the mean is 10 and the standard deviation or sigma is 3. If x is equal to 16, so we know that the first spread from the mean will be 13 followed by 16 if we go by the standard deviation. So this is 7 and this is 4. Subtract 3 each time. So because our value is x equals 16, we can find x equals 16 right there, which is 2 standard deviations away from the mean, isn't it? In that case, we can say that the z-score of 16, when we change it, when we standardize it, that's 2. 2 standard deviations away from the mean. That's how far 16 is from 10. It's 2 standard deviations away from the mean. And this is pretty useful because if we know the distance in terms of standard deviation, we can tell whether it's in the typical zone or it's in the unusual zone without worrying too much, because just by looking at the number 16, it's sometimes hard to know unless, especially if if the mean and standard deviations are as not as nice as these numbers. They're like decimals or large numbers. Um, and it's another way, another benefit for this is to actually compare different data, which will be part of our example today. Okay, I think I said a lot of stuff about that. Okay, how do we standardize? We standardize using a formula. So we standardize a value using a formula, and that's the formula you see here. So to get what we call the z-score, we pronounce this the z-score, we actually subtract the value. So this value here, that's actually x minus the mean, which is mu, divided by the standard deviation sigma. So for our example, we know that the mean is 10, the value x is 16. Take away the mean, which is 10, and the sigma is 3. That kind of gives us 6 over 3, and that's where the 2 came from. Okay, so we know it's 2 because it's exactly lined up on the second standard deviation. But using the z formula, it's 2 as well. Okay, so that kind of works out to our favor over there. All right, any questions about z-scores? Because we'll head towards another set of examples which will clarify how to calculate it, at the same time why are we doing it. Okay, so let's check our understanding. First question, suppose that you took a test, and let me know if you have some questions. Suppose that you took a test and you score about 80 out of 100 possible points. So this is your score. So this is you. Now, you also have, your class has a mean of 75 and a standard deviation of 10. So you score, which is your random variable, your random data is 85. And the average of the class is 75. You definitely scored higher than the average of the class. And the sigma of the class is 10. So the score seems to be spreading by 10 from 75 from the center. Now you have a friend took a different test and scored 16 out of 20. So definitely not the same test as you did. And the mean of the class for your friend is 10 and the standard deviation is 5. So for your friend, the x is 16, the mean is 10, and the standard deviation is 5. So those are the important portions, important given, because we know that we need all of those in our z-score formula. Now the question is, who performed better? Did you perform better because you're 10 points higher than the mean? That's what you got right here. So you're 10 points higher. And while your friend is only 4 points higher, not 4 points, 6 points higher here. Is that how we will objectively compare data? So of course the answer is no. So we have to have a better, more objective way to do that. Let's take a look at some of the sub questions before we make some generalizations or conclusions about this. So if you look at this, question is who scored better. First question, um, let's look at the percentages. So we know that a percentage scales both scores to a score out of 100. So we can check how much percent did you get out for your test, and how much score did your friend get in their test. If you look at your score, so at least for you, you scored about 85 out of 100. That's 85%. While your friend scored about 16 over 20. I think that's 80% if I'm not mistaken. Let me just double check that. Yeah, that's 80%. So on the onset, you would say, oh, I scored higher because it's 85 out of 100. And that's a higher percentage, isn't it? So, well, in terms of score, it is the higher percentage, but I'm not sure if that's what the question is really asking about entirely, who performed better than whom, because both classes have different standard deviation. So we might need to take into consideration um, your score and your friend's score relative to the whole group, the performance of the whole group. So let's try that. I think that's letter B. So who scored relatively higher relative to their classmates? So now we're looking at, is 85% a good score? Because it's not necessarily a good score if all of your classmates got around 85 as well. So that's going to be like, it's an easy score. It's an easy quiz or an easy test. So we have to look at the performance of the class as a whole, because if we don't take into consideration like standard deviation and the average of the class, it will be deceiving. If we just look at it, will be a little bit deceptive, because for all we know, everybody got, you know say for example, if every got a perfect score, 85 over 100 is really not that good. You get what I'm saying? So we have to consider the whole situation. Okay, so we have Z is equal to X minus mu over sigma. So for the first situation, we have 85 is your mean. 75 is the mean. 85 is the score, and 10 is the standard deviation. So for us, we have 85 take away 75 over sigma, which is 10. And that is about 1. What does that mean? So when we standardize your score from the center, which is 0 standard deviation, you are 1 standard deviation above the mean. So you perform, that's really good. It's very good. That's very high. It's 1 standard deviation above the mean. Okay, so how about your friend? Okay, so your friend, Z equals X minus mu over sigma. Your friend scored 16, if I'm not mistaken. So 16 minus 10 over 5. So 16 minus the mean over the standard deviation, which is 5. That's about 6 over 5, or 1.2, 1 and 1/5. So 1.2. Your friend actually, compared to her classmates, scored a little bit higher, performed a little bit better. Because within her own class, she is 1.2 standard deviation away from the average of the class. However, the 85% earlier, which is our score is 1 standard deviation above the average of our own class. So if you compare performances, it would seem that your friend actually outperformed us, because relative to her own class, she's further away from the average. She's way, way higher compared to us, which is only 1 standard deviation, but your friend is 1.2 standard deviation. So that's a more objective way to look at this problem, because we are now comparing our performance with the rest of other performances within our own classes. And similar to my analogy earlier, taking the percentage might be a little bit of deceptive, because in a class where everybody got a perfect score, that 85% is really not that good. It's really not that fancy. So we have to take into account the mean and the standard deviation. How far is our score away from the center, from the mean? And that's the best way to actually look at the who performed better than whom. Any question? We okay with that? And I just quickly look at the chat box, because there seems to be. Oh yeah, yes. So some of the additional stuff there. Okay, so no questions so far. So let's formalize it. What is a standard normal distribution? At the end of the day, we want to talk about the standard normal distribution. It's a normal distribution, with the center uh, of mu and a standard deviation of sigma, and we used to write it as mu sigma last time. The main difference is for it to be considered a standard normal distribution, it should have a mean of 0 here. You could see that. And the spread from the center or the standard deviation is 1. So if you have a normal distribution centered at 0 with a sigma of 1, basically n01, remember this is the mean and this is the sigma, then this is what we call a standard normal distribution. So this one is your standard normal distribution over there. Okay. Any other distribution is not standard. For example, this distribution here, this is not a standard normal distribution because this is an n centered at 10 with a standard deviation of 3. So that is not considered standard normal distribution. It's just a regular normal distribution. Okay, but this one is considered standard because it's centered at 0. The mean is 0 and the standard deviation is 1. So that's a distance of 1 over there. Okay, any questions so far? Before we go to a lot more other examples, this type of a lesson requires us to look at certain examples and break it down. It's more of learning by doing. So if you have your handbook with me,
I have one question. I'm
sure.
sorry.
Go ahead.
So
No, no.
for
Yeah.
for B, so basically the friend performed higher with a standard deviation of 1.2.
Yes.
Okay.
Yes. So for letter B, to answer letter B, sorry about that. So who scored relative to your friend? So your friend basically scored better. Let me delete that box there. So your friend, yeah, your friend has a higher z-score of 1.2. So hence performed better. Performed better. Apologize for the bad handwriting. It's a little clunky pen. I think it does its job well considering the circumstances. All right. Thank you for asking that question. Any other clarification from anyone? So for questions that require you to compare performances, we look at how far they are from the mean using z-score or standard deviation. The bigger the standard deviation, the further away from the mean, whether it's positive z-score or negative z-score. In this case, the further away, the higher the score. The higher the score, because the center is the average. What not necessarily what everybody got, but what the average of the class is. All right, so let's go to more examples. Okay. First question, I mean, actually it's number 2 already. Use empirical rule. If you forgot about that, that's the official name for the 68, 95, 99.7 rule. We have 68% for the first standard deviation, 95% for the second standard deviation from the mean, and 99.7% of the data are found within 3 standard deviation. That's almost everything. So that's 99.7 if you have the third standard deviation away from the mean. Okay. All right, so we'll use the empirical rule and the standard normal distribution. Remember that is centered at 0 with a sigma of 1. Okay. To answer the following question, how much percent, so this is the question now, what is the probability? So that P represents probability. What is the probability if your z-score is between -1 and 1. So we're kind of looking at this area here. So that's a z-score of -1 and 1, isn't it? Because this is a z-axis here. It's already standardized, so we're not using x anymore. So from z equals -1 to z equals 1, how many percent is that? You remember? From last class? So remember,
68%.
what was that?
68%.
Yeah, yeah, that's true. And it is 68%. Okay, so, oops, I erased this thing here. It was left over from the previous class. All right, this is 68% by empirical rule. Letter B, what is the probability if the z-score is more than 1 standard deviation? Okay, let me erase this. We're now looking at the area beyond 1 standard deviation. So we're looking at this part. Okay. I think this is a bit similar to what we've been doing last time, but because we kind of like had a similar question. So we know this is 68%. Agree? That's 1 standard deviation from here to there. How many percent will it be if we split 1 standard deviation into half areas?
16.
Oh, you're referring to this one already. Yeah, that will be 16. Actually, that's true. Well, let's break it down some more. Feel like ahead of the game here. So if this is 68%, we can break this into 34% here and 34% there. So that still adds up to 68%. So the 34% is part of half of your normal distribution, okay, which is about 50% of the data. So this entire thing here, both of them included. So how did we get 16% here? So 50% take away 34%. That's 16%. So isn't it crazy? It's already too small. 64 beyond the 64%, the tail end starts to decrease in amount of data. It's only 16%. After 1 standard deviation, it's only 16% here. Yeah. You can also use the little cheat sheet that we provided last time, this one. So if you add all of these by the tail beyond the first standard deviation, it's about 16% approximately over there. Okay, so we got 34% here and here, making up the typical values of 68%. Okay. So this is very useful. Normally we can find this printout in the math lab, but math lab is closed, so I just put it here in the PowerPoint. Okay, good. So that answers letter B. You have 16% here. So far, so good. We're doing really well. All right, how about between 2 standard deviation? I think we don't even need the drawing for this. You can just tell me what it is. How much data are found between 2 standard deviation of the normal distribution? Using the
Is it
empirical.
95%?
I don't know.
95. Did you say 95%?
Yeah.
Yeah, 95% is correct. So from here to here. So from -2 to 2, 95% of all the information or your population is found here. It's a lot of data. If it's people, it's 95% of the people are found there, except for a rare few that are by the tapers, by the tail end. So less than -2 is the next one. Okay. Let me go back there. So we're looking at last question, less than -2. So this is the normal distribution. Z equals -2 is found here. Starting here, we want everything less. So what percent of the population is represented by that group, which is less than 2 standard deviation? Any guesses? So remember, give you a clue. This is already 95% within 2 standard deviation. That's already 95%. So if this is 95% that I'm coloring right now, I enjoy coloring it. So I'm coloring right now. How much percent is that little yellow tail? Because that is exactly the same amount of percentage here.
2.5.
Yes, 2.5. So there has to be, like, again, I think this is the third time I said this. There is a 5% left over that needs to be shared by the two tails. Because a probability distribution and normal distribution, they always add up to 100%. So that is 2.5%. Very good.
So to get that 2.5, you take 100 minus 95 and then divide it by
Correct.
2.
Correct. So we subtract that. There's a 5% left over, but because it has to add up to 100%, it needs to be shared by the two tails. So, 2.5 here, 2.5 there. That adds up to 100%. Okay, and we can always look at the cheat sheet. So you could see these two. That adds up to 2.5%. Okay. Because 2 standard deviations essentially is from here to there. So these portion, it's 95%. Okay. All right. Oh, there is a question number 3. Oh, this is a chicken egg problem we did earlier this morning with my other class. So suppose that the distribution of chicken egg weight of the chicken eggs is normal. It's normally distributed. If you collect all the chicken eggs and measure their weights and make a distribution out of it using StatCrunch, it will end up having a shape of a normal distribution. What are the other information we know? We know that the mean is 0.2. I mean, not 0.2, 2 ounces. Well, you can see it here. That's the mean. Now, the standard deviation of the measurements of the whole population of chicken eggs is 0.3. So let me just write that. The sigma is 0.3, right? We have been provided with the normal distribution from StatCrunch. It's already available here, okay? And the question is, what is the z-score for the smallest jumbo egg? Okay. Now, what is a jumbo egg according to the problem? For it to be considered jumbo, it has to weigh at least 2.5 ounces, which is already here, okay? So this is the boundary line. So when x is equal to 2.5 or anything higher than that, we consider that jumbo. It's a big egg. Because most of the eggs, typical egg, will have weights between 1.7 to 2.3, about 68%. Typically, that's the typical value or typical range of values. So we could say that a typical egg will weigh between a 1.7 to a 2.3. But we're not interested in typical weights. We're interested in jumbo. So how do we know if it's a jumbo or what percentage, this one, what will be the percentage there of all the jumbo eggs? So let's calculate the z-score because that's the requirement for letter A. What is the z-score of the smallest jumbo egg? So we write the formula z equals x minus mu over sigma. I love this formula. It's very straightforward. It's very simple. The data are always available to us. And we know that we have x is 2.5, the mean is 2, and the sigma is 0.3. Okay, so let's kind of like plug them all in here. So we have 2.5, take away the mean, divided by sigma, which is 0.3. Okay. So we have 0.5 over 0.3. If I'm not mistaken, this is around 1.67 approximately. Checking it with my calculator. Yeah, it's the same. So that's our z-score. This is our z-score, 1.67. Any questions on how to calculate the z-score? That's one of the requirements for letter A. We need to calculate the z-score. The next question is, what does the z-score tell us? Does anybody remember what does it tell us? What does a z-score mean? That's 1.67. It indicates that it's 1.67 deviation away from the mean. So that's the standard deviation. It's not in the unusual zone. Yeah, well, definitely some of them will be unusually high because it has to go beyond 2 standard deviation, but it's getting there. If it's 1.67 deviation, we will consider that jumbo egg. Okay, so the z-score tells us its distance from the mean is 1.67 standard deviation. Okay. Show that the z-score, looking at the next question now, this is the third question. Show that the z-score on the probability distribution of egg weights. Well, okay, we kind of mark it here already. It's not the standard normal distribution though. Okay. But this is a z-score of 1.67. If it is 0, standard normal distribution of 0, so that's 1.67 away from the mean. Okay. In the original graph, this if the normal distribution, standard normal distribution, I'm sorry about that. In the standard normal distribution, for it to be considered jumbo, it has to be around here, 1.67. So anything above that is considered jumbo egg. Okay. So it has to be that far away. Now, some of them are unusually high. So anything beyond 2 standard deviation are unusually big egg. So, all right. Are unusually heavier also. Okay. So let's go back to think that answers letter A completely. Let's take a look at letter B. What is the probability that a randomly selected egg is classified as a jumbo egg? So we already kind of knew the z-score there. We know that the z here is 1.67, but we don't know the percentage there. We don't know how many percent of all the eggs collected by whoever's selling these eggs are considered jumbo in weight. So what are the things we need to do here? We will use StatCrunch and the standard normal curve to actually um, analyze that. Let me just log in very quickly. Thought I already logged in StatCrunch earlier. Apparently, okay, I'm still logged in. That's good. So we go back to, okay, let's just fill in the blanks first. So we will use the standard normal curve, which is this one, okay? We know that a standardized normal distribution will have a mean of 0. Okay, I'll put 0 there. So if you're following me in your handbooks, just fill in the blanks here. The standard deviation is 1 because remember, it's n01. It is centered at 0 with a standard deviation of 1. Okay, so this part. We're looking for jumbo egg, which is definitely more than 1.67 here. Where at this point, we're using z now. Okay, so we're trying to find out this part. Okay, so in this case, the x represent the z-score. So that's why I kind of like edited this as a z, but the x actually represents a z-score. All right, so are you ready? So let me go to I'll share a new screen. So you should be able to see the stat crunch. Can you see it?
Yeah.
Okay, good. So open my stat crunch. The goal of this is to be able to calculate the percentage of the shaded area represented by the jumbo egg. If you look at the graph, you won't see normal distribution there because it's supposed to be a calculation. So you go to stat, go to calculators, and if you look at the drop down menu, one of them is normal distribution. So I'm gonna click that, and you'll get a normal distribution graph. So it kind of did save the one we were doing earlier. So let me just repeat that. So it's brand new. All right. So as you could see here, the normal distribution is already standardized. Mean is 0, and then standard deviation is 1. What we want to see is quick share of the PowerPoint again. We wanted to find this area over here, where it's more than 1.67. Okay, that's the distance from the mean, the standard deviation for it to be considered a jumbo egg. So what we'll need to do is we need to put in here 1.67. Now, you have to make sure you switch this to a greater than so that it will shade the right side, because if you don't do that, it will shade the left side. So that's the less than. That's about 95%. You could see here, it's 95% of the values are lower. So 95% of the egg weights or eggs are not considered jumbo. But if you go choose the greater than, about 4.74%, 75%, so almost 5% of all the eggs are considered jumbo. So that's why when you go to supermarket, those triple A grade eggs or the big ones, they cost more than the regular eggs, because there's only 5% of them in the whole population of eggs. So that's why they're more expensive. The jumbo eggs, I mean. Okay. So uh, was it for 0.047? Okay, let me just remember that as I switch to the previous screen. Okay, so going back, we can now fill this up. And I think what we got was 0.047 approximately, or about 4.7% of eggs are jumbo weight eggs. Okay. Any question using the StatCrunch? So for this method, the method was focused on standard normal distribution. We did not make use of the information earlier where the egg has a mean of 2, jumbo egg is 2.5 and above, and standard deviation of 0.3. We didn't use it. So one way to calculate the percentage is to use the standard normal curve or normal distribution. And another one is to actually bypass standardizing it if we're using StatCrunch. So that's going to be letter C. So in letter C, we're using the regular numbers that we have from the problem. Namely, the mean is, I think, was 2. The standard deviation is 0.3. And for it to be considered a jumbo egg, it has to be at least 2.5 in here. Okay. This part. Okay. All right. So it has to be more than 2.5. Ah, 2. What are these pop-up boxes doing here? I deleted them. Okay, so 2.5. Okay. Well, in here, X, we know X represents here the weight of the eggs. They're not standard deviation or z-scores. They're the actual weights of the eggs. Okay. So the mean of the egg is 2. The standard deviation of the eggs are 0.3. We want to know how much percent are the jumbo eggs if they do measure 2.5 ounces or higher. Oh, kind of like messed that up a little bit there. So, or higher. Okay, so let me switch back to StatCrunch, our software. Okay, share. Okay, I'm gonna modify this to a mean of 2, and this one will be a mean standard deviation of 0.3. Okay, and I think we're calculating 2.5, right? It's 2.5. So it's already greater than, so there's no need to adjust it. And as you could see, we got around about the same 0.04. There's a slight discrepancy if you haven't noticed, because of rounding error. We didn't round off here, so this is slightly a better option for us. The standardized version has a little bit of rounding error, so 0.047, around the same number. We just go back to, okay, check if there's some questions over there. Alrighty, so let's share back the original one. Okay, so this is the same, about 0.047 as well, or 4.7%. Theoretically, both methods should give you the same probability. I'm reading this one. Theoretically, both methods should give you the same probability, but the answers you found may differ a bit. What adjustments could you make to rectify this situation? Usually, one of the things we could do is try to round off as many decimal places as you can. So rounding off errors, we want to minimize round off errors. Okay. Or final answers, we can set it to, like, say 5%, round up to 2 decimal places. That could kind of like rectify the situation, but it doesn't have a lot of discrepancy. As you could see here, I rounded it off to 3 decimal places, and both have essentially the same results. Okay, so we kind of like did rectify that situation. Okay, any questions so far from the class? So quick summary on how to do it using StatCrunch. First, you kind of like need to go to stat, not graph. You won't find normal distribution there. So go to stat, and you get to calculate using calculator, and open normal distribution, and then put in the values there. By the way, you can also switch to between, because you can see there's a standard and between. I'm kind of like flipping them back and forth. Okay, so between will give you the area between the two curves. You can see area between -1 to 1 is 68%. So if we switch to 2 standard deviation, because this is centered at 0, with a standard deviation of 1. So that would give us about 95%. Yeah, there you go, 95% of the data. All right, go back to this one. All right, why do we need to learn this? Why the need? Why does this have to be a separate session? Why focus too much on this one? Why do we teach the z-score and the standard normal distribution to find the probability, the shaded area? So how much percent is found underneath those, like for example, the jumbo egg problems, like 5%, almost 5%. The answer here is the z-scores will be used much later in the course. For now, we're looking at the methodology on how to standardize the data. This is more of preparing ourselves to a much bigger type of lesson in the future. Whenever we try to start sampling and what we call inferences, so when we go to what we call statistical inferences, where we pick a random sample and we try to interpret the sample so that we will have an idea of the whole population. So remember, a whole population may be really, really big. For example, there are 7 billion people in the world. We can't literally ask 7 billion people questions or gather information. That's a lot of resources. That's a lot of time. What we can do is from the whole population, we randomly pick a small segment of it, a small section, which will be our sample. Now, the sample, assuming we've done a good job randomizing that, and it may be, and assuming it is a representative of the population, then we can use z-scores and to find certain probabilities that may interpret the whole population. Okay. So this is more of preparing for that. We will be calculating what we call a test statistic. Z-score is an example of that. There are a bunch of different kinds of test statistic we'll learn in the future, but Z-score is the first one so far to learn. In order to calculate probabilities, you know, it's easier that way anyway, because we know, if we know the z-score, we know how far it is from the center. So if it's 1.67, we know that it's about that far away. If the z-score is 2.1, you know that's beyond 2 standard deviation, that's already unusually high. If the z-score is like negative 2.5, that's unusually low because it's beyond the 2 standard deviation, below the mean, which is like here. Okay, so that's part of the unusually low. So it's very helpful in analyzing different samples from the population or population. Okay, any question as of the moment? There are 16 of us. We will now proceed to a breakout session. Okay, and this is the first time we're doing it. If you have your handbooks with you and hopefully a mic, if you don't have a mic, use the chat box. I will randomize the group into 3 different groups. So there'll be more members in the group. Usually we do 4 in a group, right? So there's 16 of us. There should be a bit more than, let's do 3 groups for this. I'll kind of like stop sharing. I mean, not stop sharing, like save the video, stop recording, and then we can do the randomization. I'll explain it once we're in the group.